Hello viewers, this is the midterm project report for EE675 Introduction to Reinforcement Learning, and this is presented by Devrat Bothra, Rahul Jha and Shivansh Pandey. Okay, so our problem statement is that we are given a graph which is represented as G, and this G equals to V comma E. V is the vertices which are V1, V2, V3 etc. here, and E is the edge connecting each vertex. So we have to find the maximal independent set. So let's understand what independent set is. Independent set comprises of those vertices whose adjacent vertices are not present in that independent set. Like the formal definition of it goes as an independent set is a set of vertices in a graph, no two of which are adjacent. That is, it is a set of vertices such that for every two vertices there is no edge connecting the two. Equivalently, each edge in the graph has at most one endpoint in. So for example, let's say if that set contains V4, so V1, V2, V6 and V7 won't be present in that set. So we can make an independent set like V4, V5. As we can see that V4 and V5 are not, hence they make an independent set. So we have to find a maximal independent set. As we can see that V4 and V5, the independent set that contains V4 and V5 is not the maximal independent set, because maximal independent set means that this independent set with most elements is the maximal independent set. So V3, V4, V5, this set is our maximal independent set for this graph. And similarly, it can also be that V6, V1, V5, these three also make the maximal independent set. So for maximal independent set, we don't have one unique solution. So we have to find this. We have encountered with various algorithms for it, like Luby's algorithm, but now we are trying to use reinforcement learning to solve this problem.
So I will be briefing the contents of this research paper which we have reviewed. The paper introduces to combinatorial optimization. It focuses on complex computational problems such as the maximum independent set, satisfiability, SAT, and the traveling salesman problem. The relevance of this problem is that these appears across various fields like sociology, bioinformatics, and operations research. The challenge about this combinatorial optimization is that most of these are NP hard, making exact solutions difficult to find. Now, let's talk about the evolution of solution methods. Traditional approaches relied on heuristic solvers for an approximate solutions. Now, advancement through AI has led us to shift towards deep neural networks for developing learning-based heuristics, moving from supervised to unsupervised learning models. With the introduction of deep reinforcement learning, also known as DRL, the DRL uses the Markov decision process. Markov decision process framework for training models to tackle combinatorial problems without pre-existing solutions. The current limitations of this is that it struggles to match the performance of highly optimized traditional solvers, especially in complex high-dimensional problems. Learning what to differ framework, also known as LFD, optimizes decision-making over multiple steps, focusing first on simpler decisions to facilitate more complex ones. The performance demonstrates superior results, outperforming both traditional and state-of-the-art solvers in large-scale tests. Talking about empirical validations and applications. It has been tested across various graph models and real-world scenarios, showing consistent superiority over traditional methods. Broad applicability for future research and practical applications in other optimization challenges is one of its potential. Coming about the LWD framework. The learning what to differ framework addresses the maximum independence set MIS problem by strategically differing decisions about vertex membership in the solution set, which allows for more efficient problem solving. As you can see, the figure 1 here is an illustration of the proposed Markov diffusion process. The initialization is as follows. Each vertex starts at zeros, undetermined, represented as 0, which is excluded feature, then 1, which is included feature, or star, which is known as default. The iteration agent iteratively decides the membership for each vertex or defers the decision to later iterations until all are determined. Its strategy prioritizes easy decisions first, simplifying more complex decisions later. The MDP formulation combines an MDP framework with a policy to generate solutions where the state represents vertex membership and actions determine new membership assignments. Transitions between states involve updates and cleanups to ensure valid confirmations, addressing vertex adjacencies approximately. The model uses a cardinality reward based on the number of vertices included in the independent set after each action. Diversification reward. Diversification reward in diversi- diversification reward. Diversification reward introduces a diversification reward to encourage generation of variety of solutions, enhancing the overall effectiveness of the model. Training the model utilizes proximal policy optimization with a policy network and value network to optimize the learning process based on the rewards and state transitions. LWD is designed to be more flexible and efficient compared to traditional combinatorial optimization methods, including those that rely heavily on heuristics or intensive computations. Talking about the Markov decision process and explaining how it works. Each node, the value of the state is 0, 1, or star dash. 0 is excluded from maximum independent set. 1 will be included from maximum independent set. And star is deferred, i.e., it will be decided later. The action is only taken on deferred state. Action would be to assign 0, 1, or star following a policy. Then transition would be on updated phase and cleanup phase. The reward is the sum of cardinality reward and diversification reward. Training with proximal policy optimization. Training with proximal policy optimization. The training is based on actor critic. It has a policy network and a value network. The graph stage architecture is as follows. The loss function is described with the following equations. Of policy regularized deep reinforcement learning, the regularizer function is as follows, and the loss function is defined as this. Here actions are -1, excluded, 0 deferred, and 1 included. The paper 2 briefs about the wireless link scheduling is crucial for selecting optimal sets of data transfer and links each communication slot to maximize a utility metric. Its application is key in time critical wireless applications like dense mmWave cells and wireless backhaul networks. The technical challenges is that scheduling involves solving the maximum weight independent set MWIS problem on a conflict graph, which is NP-hard. The challenges in existing solutions are the existing heuristic algorithms for MWIS are memory intensive and slow for large graphs. Greedy algorithms, simpler but less effective, often fail to find near optimal solutions for dense graphs. Deep reinforcement learning is an emerging solution where an agent learns to solve MWIS via Markov decision process MDP, enhancing independence from domain knowledge, but with drawbacks in data efficiency and value overestimation. To overcome this, the proposed off policy RL algorithm is introduced. Introduction of an off-policy regularized RL algorithm using clipped maximum a posteriori policy optimization CMPO to solve MWIS efficiently. This new method is robust, data efficient, and converges faster than on-policy methods. The proposed algorithm shows a 60% improvement over standard greedy algorithms, 70% heuristic solvers like KAMIS, and significant improvements over other RL-based solvers. The numerical analysis demonstrates superior performance in terms of efficiency and outcome. It also has its applications to network link scheduling. Some of its future work includes exploring further enhancements in algorithm efficiency and potential applications to other complex network scheduling problems. Problem formulation for the wireless link schedule. Conflicting graph model utilizes a graph. Problem formulation. The conflicting graph model utilizes a graph noted by G, which is equal to L, omega. Here, L is the set of vertices of G of the graph representing the links of the wireless network, and gamma are the edges of the graph, represents the interference relations between the links. An edge between two vertices indicates that their corresponding link interferes when transmitting simultaneously. The time is divided into discrete slots indexed by T, where each slot allows a specific link activities without interference. Each link K has a utility demonstrated. Each link K has a utility U, which is demonstrated as U is equal to R times Q. Combining the rate of successful packet transmissions R and the Q length Q. The rate R follows a uniform distribution up to a maximum rate. A schedule for slot T, gamma T, is a binary vector where gamma T is equals to 1 if link K in L is included in the schedule, 0 otherwise. The objective is to maximize the sum of utilities of active links. The constraint is to ensure no two interfering links are active simultaneously, which effectively makes the problem one of the solving maximum weight independent set on the conflict graph. Talking about the algorithm, the MWIS problem is modeled as Markov decision process, MDV, where each vertex of the conflict graph is given a label 1, 0, or -1, representing its inclusion, undecided status, or exclusion from the MWIS. The state of the MDP at any round n consists of the subgraph of undecided vertices. Actions involve assigning labels to vertices. Transitions depends on these actions and include cleanup steps to ensure no neighboring vertices are both included. The reward measures the change in the sum of weights of the vertices, including in the MWIS from one state to the next. Off-policy optimization utilizes historical data from past policies to improve the current policy, enhancing data efficiency and reducing value overestimation bias. Regularization with CMPO uses a clipped maximum, a posteriori policy optimization regularizer to manage the variational distances between prior and updated policies, maintaining policy integrity. The loss function combines policy gradient loss, CMPO regularizer loss, and value loss to optimize the policy network and the value optimization. The algorithm is executed in the following way. First, we initialize policy and value network parameters, collect data using prior policies. Using replay buffers for training batches, calculate loss, and adjust network parameters through gradient descent. Then compare performance against benchmarks like greedy algorithms and state-of-the-art heuristic and RL-based solvers. Graph neural network implementation is done as follows. The GNN architecture utilizes graph convolutional layers to process the state of each vertex, learning from the network's topology and vertex features. The action prediction and value estimation implements separate networks for policy action prediction, and value estimation, the latter using global pooling to summarize state values. Hyperparameter details and pseudocodes are as follows. These are the proposed algorithm to determine and
So our first proposed solution is that we are going to group this whole graph into number of groups that we are going to predefine it. Okay, so we are going to select seed points which will be selected randomly. We are going to give that number of seed points as our input, and we can make it as a function of the number of nodes of whole graph, so that if the number of nodes get increase very much, then the seed points will increase simultaneously. So like here we can see that the graph is divided into 4 groups. One is blue, one is light blue, one is red, and the other one is green. So first we are going to give seed points, and then we will use any algorithm to determine the groups. Like one seed point, then its neighbors will be on that same group, and eventually those groups will be formed. So after this, once our group is formed, we are going to again use the same algorithm which we saw earlier, that off policy regularized deep reinforcement learning, on each of these groups. Now here one limitation can be that the boundary points can be affected. Like for boundary points, it is possibility that two adjacent nodes can have the values -1, -1, or 1, -1, or 1, 1. So for -1, -1 and 1, -1, we don't have to change our values, but for 1, 1 we need to change those values, because both are included in the same independent set. So once we get that boundary edges, like for boundary edges I mean that a node whose adjacent neighbor in another group, so that edge is cutting that boundary of those groups. So for that 1, 1 edge, we are going to assign the value 0, 0 to both of the vertices. Now once we have assigned those values, we can again do that same algorithm of policy RL on that whole group which has 0, 0 values. It's just like that. Once we are done with the groups, we are going to clean up the whole graph, and again we are going to use that algorithm to get our independent set elements. So once that is done, the superset of all these groups, like we are going to take the union of all the groups and the union of that boundary point group as our maximum independent set. So this is our first proposed solution.
So I am going to propose our second solution, that is max plus algorithm. So our problem statement was to select nodes in the graph such that no two selected nodes are directly connected. That is, they form an independent set, and the selected set contains the maximum number of nodes possible. We can implement multi-agent reinforcement learning using the max plus algorithm to solve this problem statement. This approximates the optimal joint action by iteratively sending locally optimized messages between connected nodes in the graph. Since any arbitrary graph can be converted to one with pairwise dependencies, the global action value function can be decomposed into pairwise value functions given by qs, a is equals to summation of I, j belonging to the entire graph space qij sub s ai aj. So ai and aj are the action of agent I and action of agent j, and qij is the Q value function of that particular pair of agents. Next, while in state S, a message from agent I to neighboring agent J describes a local reward function for agent J and is defined by. So this is the local reward function, or we can say the message which an agent I is sending to its neighboring agent J, for which we are using the multi-agent reinforcement learning, is mu ij based on action taken by agent J is equals to maximum upon action taken by agent I. And of what we are taking the maximum, it is Qij state of at action taken, action AI taken by agent I, and action J taken by agent J, plus summation of mu Ki on AI, that is action taken by agent I, and this summation is going from K belongs to this set, and this set is all the K's except J, because we are taking the message from J between J and I, so we will not include J in this part, plus Cij. Max Plus has been proven to converge to the optimal action in finite iterations, but only for tree structured graphs, not those with cycles. Nevertheless, the algorithm has been successfully applied to such graphs. So yes, now we are talking about the message which an agent J sends to agent uh, I, we can say. So the set which I was saying that denotes all neighbors of I except for J, and Cij is either 0 or can be used to normalize the messages. The message approximates the maximum value agent I can achieve for each action of agent J based on the function defined between them and incoming messages to agent I from other connected agents except J. Once the algorithm converges or time runs out, each agent I can select the action. So this is the optimal action which an agent will select. That is AI star is equals to arg max AI I belonging to the set of uh, I belonging to the set of action space mu ji based on action taken by agent I. So we'll maximize this upon action taken by agent I, and then we will get the optimal action. So yes, now we can approach this problem using multi-agent reinforcement learning and the Max Plus algorithm in the following steps. So first we need to initialize, that is we need to start with an empty set as the current solution. State representation, represent the state of the environment as the current configuration of selected and unselected nodes in the graph. So I will explain this with an example. Let's consider this to be a 2 cross 2 graph with nodes numbered from 1, 2, 3, and 4. Say if a node is selected, it is assigned the value 1, and if not selected, it is assigned the value 0. So say we are selecting node 1. So here the value will be value assigned will be 1. We are not selecting node 2, so the value assigned here will be 0. Suppose we are also not selecting the node 3, the value assigned will be here 0. Suppose we select by chance the node 4. So here the assigned value will be 1. So what I am saying is that our state S at time t, that is st, can be represented as a number assigned to node 1, number assigned to node 2, number assigned to node 3, and number assigned to node 4. So it can be possible combinations of 1 0 0 0, or it can look like any of these three, or the other combinations which are possible with all being 1, with all being 0, with 3 being 1, 1 being 0, with 2 being 1, and 1 being 0. Other two being 0. So let's say we assign value 1 to this node 1, we assign value 1 to node 4, we assign value 0 to node 3, and we assign value 0 to node 2. Then our ST will look like 1, comma 0, comma 0, comma 1. Now, talking about action space, for each agent I, the actions can be defined as follows. That is, we are taking at any point of time, we are taking two actions. That is, we are either including a node or we are excluding a node. So the include action. The agent selects its corresponding node to be included in the current solution. Exclude. The agent chooses not to select its corresponding node, excluding it from the current solution. So taking an example of action space, let's say for an agent, say 3, we can take two actions. Either it can select node 3 for the solution set, that is node 3 is assigned a value 1, or it may not select node 3 to include it in the solution set. That is node 3 is assigned a value 0. So assigning a value to a node is our action, we can say. Now, talking about the reward structure. We can define a reward structure that encourages agents to select nodes such that the resulting set forms a maximum independent set, which is our ultimate goal. So let's say we are including a node. So what should be the immediate reward for including a node? If an agent selects a node to be included in the current solution and that node does not have any adjacent nodes already selected, that is not connected to any selected node, the agent receives a positive reward. This encourages agents to select nodes that are not adjacent to any other selected nodes, contributing to the independence property of the set. If an agent selects a node to be included in the current solution, but that node is adjacent to at least one other selected node, the agent receives a negative reward. This discourages agents from selecting nodes that violate the independence property. Now, let's say we are excluding a node. So what should be the immediate reward for that? If an agent chooses not to select its corresponding node, it receives a small positive reward. This encourages agents to explore different combinations of nodes and actions, even if they ultimately decide not to include their node in the current solution. Now, talking about the end of episode reward. At the end of each episode, that is after a certain number of steps or when a terminal condition is reached, the agent receives a reward based on the size of the selected set. If the selected set forms a maximum independent set, that is, it contains the largest number of nodes where no two nodes are directly connected, the agent receives a large positive reward. Otherwise, it receives a negative reward proportional to the size of the selected set. This encourages agents to strive for larger and more independent sets. We can also give an exploration bonus. Optionally, agents may receive a small positive reward for selecting nodes that have not been explored extensively in previous episodes. This encourages agents to explore less explored regions of the solution space, leading to better exploration and potentially improved convergence. Decentralized learning. Each agent maintains its own Q value function as shown in the previous slide that we are defining Qij S, AI, Aj. That is, Q value for a pair of agents is defined based on the state and the action taken by agent I and the action taken by agent J. So this represents the expected cumulative reward for selecting a node given the current state of the environment. Agents update the Q values using the max plus algorithm, considering the maximum value over all possible next states. Exploration exploitation comes as the next step. Agents employ exploration exploitation strategies for say we can use epsilon greedy. So let's say we find an optimal action AI star for an agent AI, then we can choose it with epsilon probability, and we cannot choose it with 1 minus epsilon probability. We can use this epsilon greedy algorithm to allow our agent to explore more new options, more such options which are not chosen yet. So to balance between exploring new node sections and exploiting the current knowledge to maximize rewards. Now, training. Train the agents through interactions between the environment, allowing them to learn decentralized policies for selecting nodes that form a maximum independent set. Evaluation. Periodically evaluate the learned policies to determine the effectiveness in funding large and valid maximum independent sets in the graph. Sorry. Hyper parameter tuning and optimization. Fine tune the parameters of the max plus algorithm, reward structure, and exploration strategies to improve learning performance and conversion speed. So, concluding, by applying the max plus algorithm with the MARS framework, we can enable multiple agents to learn decentralized policies for selecting nodes in the graph with the collective behavior aimed at discovering a maximum independent set. This approach leverages the strength of both reinforcement learning and graph theory to tackle a combinational optimization problem. So, I got to know about this max plus algorithm and its usage in multi-agent reinforcement learning from the research paper Multi-Agent Reinforcement Learning for Urban Traffic Control Using Coordination Graphs. Thank you.
Okay, so let's now discuss the pros and cons for centralized and distributed solution. The pros are mainly for the scalability. That is, distributed solutions can be more scalable than centralized solutions, particularly for large scale graphs with a high number of nodes. Each node in a distributed solution can operate independently, leading to better scalability in terms of both computation and memory requirements. But there are cons as well, like the complexity of the solution increases as we go to the distributed solution. Hence, our computation time also increases for this. And also, it becomes more robust to the failure, as distributed solutions can be more robust to the changes in the network topology compared to centralized solutions. Since there is no single point of failure, the system can continue to function even if some nodes fail or become disconnected from the network. So these will be our limitations, and we would have to focus on the cons as well while programming our system. These are the references that we used, and thank you very much.